Okay. Okay, so I'd like you to close out the current model. And now I'd like to add in a new model. Okay? New model. And this will be a model called crowding disparities, or call it SIRS, crowding disparities. Okay? And in contrast to the previous model, whose time units were in years, we're going to use a different yardstick here. It's going to be days for this model. Okay, so, ladies and gentlemen, we're going to measure time in days for this model. Okay, so, having done that, we're going to do finish. And now, we're going to go through our normal little familiar steps in setting up a model. Sure. Okay, Ellen, maybe when Vivian comes back, you can help her get caught up. Okay? If you could keep track of the next few steps, because she won't be able to see it here. Okay? I'm not sure, but probably won't be long. Okay, so ladies and gentlemen, we want to add person to this population. We want to have a theory of personhood. So what do we need to do? We have to create a new agent type, and it's going to be called person. Okay? We want to associate that person, once again, with a person shape. Alan's helping. All we've done is one thing. All we've done is add a person class, Vivian. Okay, I right-clicked on this, and I did new agent type on the model as a whole.
Oh, the model as a whole. Okay, that's where I got
New agent type, because we're adding it to the model as a whole. We're not adding it to main. Yeah. Yeah. Yeah, you'll see it some more tomorrow and the next day, in fact. Okay? That's one of the things about these boot camps, doing again and again and again and again the same basic steps helps you realize, you know, the basic repertoire can become strong. You build up those muscles. Okay, so we've added in person. We want to add a representation that's a little person. Where do we go?
Go to age.
Okay, well, we'll go to person, and how are we going to add that? From whence will this image come of a little person? Palette, where in the palette? Pictures. Down at the bottom. Okay, we're going to drag this in. Here's person. Here's an image for person, okay? Great. Okay, ladies and gentlemen, we are going to now create a population of people. Notice again, once again, I gave them an appearance before creating a population. So now we want to create a population, ladies and gentlemen, of people. How do I do that? We want to create a population. Where does that population live? In Maine. It lives down Maine. Okay?
Remember now that we've done a few steps to do a build?
Yeah. Good point. You could do a build here. Okay. Ladies and gentlemen, I would like to then drag person into Maine to create a population. I'm going to call it population, but does that make it a population by itself?
No.
What do we need to do? Population of agents. Okay? Suppose we want the population size to be dependent on a parameter. What do I need to do? Suppose we want to change from experiment to experiment the population size. What do I need to add to the model? Parameter, because a parameter will let us vary that from experiment to experiment. So to add a parameter, where do I go? Go to the agent palette, and if I want to vary that parameter from experiment, to what do I need to add it? To main, indeed. So let's add this into main. This will be called population size. Okay? And in this case, we're going to have a closed population, so we're not going to have it varying. Okay. What sort of type will it be? An integer indeed. An integer, ladies and gentlemen. And its default value, Winchell? Oh.
Don't kill yourself.
Its initial value be 100. Okay? Does that make it by itself, if we set population size to be 100 with a value of 100, what do we need to do to make it operational?
Put it in our population.
Yeah, put it for the population, put initial number of agents to be population size. Okay? Are we okay with that? Okay, finally, we want to show these people spread out over space. How do we do that? Good. For the initial location, specified point, what are we going to specify for x? We'll do it between uniform between 0 and the space width. So basically what's going to happen is this space width, you'll notice you can read about it here. It's going to, come on, don't give me that. It's going to, okay, let me just get it to type. Hey, come on. Here, if you say space width, it returns the current width of the environment. So whatever it is, it's going to return it. And we can use it. Okay, do we need a semicolon or not? No, because we're just determining a value. So it's going to get the space width, maybe this is 1,000, and it will do a draw from a uniform distribution between 0 and 1,000 to determine the value of x. Or space width is 500, it would draw that uniform value between 0 and 500. Okay? Okay, well, okay, now for y, we're going to do the same thing, but with space what? Space height. Okay, great. We don't want those extra things. Okay, there we go. Ladies and gentlemen, let's run this model. Let's run her. Okay? Run. Okay? You should get something like that. Okay, who wants me to show something I've done? Who would like me to show something that I've done? Anyone? Anyone? Okay. Ladies and gentlemen. Okay, so in short, in the population, we made it a population of agents. The population of agents is given, the size is by population size. Population size is an integer parameter with default value 100, right? This population is a size population size, and then for initial location, we use this. And I'll put it up on the big screen if you want to see it. Okay. Ladies and gentlemen, are we okay? Okay? Sorry? Okay. Now, ladies and gentlemen, we're going to take this in a slightly different direction. Okay. So, okay, ladies and gentlemen, I would like to, okay, great. Ladies and gentlemen, I would like to now associate this person with an income. Okay? How do we associate them with an income, a person? Actually, I'm sorry, just in the interest of time, we're going to keep things as simple as possible. I want to get to the point where we can have transmission of infection by 4:15. Okay? So this is what we're going to do. We're going to dispense with the income and the disparities and so on, which is really interesting, but we can do that tomorrow if there's interest. Right now, we're going to do something very straightforward. So, in main, rather than adding income, if you've already done it, don't worry about it, we just won't use it. Go to projects, and in main, ladies and gentlemen, I would like to go click on main, and I'm going to show you something that you probably have not looked at before in this boot camp. And that is, you will go down in main to space and network. And for the network type, See where it says network type? I would like you to put in distance-based. And the value, the connection range, is going to be 75. We're going to connect a given pair of people, A and B, are going to be connected if and only if A and B lie within 75 units of distance of each other. Now, you may ask, what does this distance represent? And you'll find, while I don't have time to go into it at this late hour, I'd be glad to talk about it tomorrow. You'll notice that there's actually a distance scale defined in AnyLogic that gives a way to convert between the scale visually, which is what that 75 is in on the one hand, and actual meters on the other. And we may use that tomorrow, okay? But for now, in Maine, we are going to scroll down and we're going to set the network type to be distance-based with a connection range of 75. Okay, are we okay with that? Ladies and gentlemen, we will now go and we will go to person. Well, okay. Right. Okay, ladies and gentlemen, we are going to go to person, and in person, we are going to go to the shape body. Do you remember how to get to shape body reliably? Sorry? Presentation, under person, shape body. Okay. Now we're going to make, it's under person here?
Oops, under person, okay.
Yeah. Okay? And we're going to set, ladies and gentlemen, their scale X and scale Y according to the number of connections that they have. Okay? Okay. So I'm going to do this to prove a point. So the scale X will be, ladies and gentlemen, it will be 5 times 5.0 times log of 1.0 time plus, okay, plus this dot get connections number. And I'm going to actually put 5.0 plus this. So it's a minimum of 5, and then as they have more connections, their size will get larger. Their scale will get larger. Excuse me, this is scale. So we actually we want this to be 1.0, excuse me, not 5.0. I'm used to dealing in terms of width of a thing. And really this should be a function, but we don't have time right now, so I'm just going to put it in here. And this troubles me greatly. It's 1.0. Okay, are you ready? So what if they have no connections? They're connected to nobody. What will their scale be? Scale will be 1.0. If they have, by contrast, a large number of connections, the log of 1 plus this will be large, and therefore that will tend to dominate this 1. Okay? Are we ready for this? Okay, ladies and gentlemen. Okay, I would like to go and I would like to run this thing. And you should see something like that. Who are these people we see before us? Who are the larger people? Who are the smaller?
Large are the ones close to a lot of other people.
Close to a lot, and then there's smaller ones who are connected with fewer. So the question is, okay, so they're connected in a network. I would tell you they are connected in a network. Where is the network? Well, in order to show it, we just need to do something. The network is there. The network was imposed, ladies and gentlemen. When we went to Maine, we said connect people if they lay within 75 units of each other, a given pair of people. The network is there, and we have set their shape, their scale, to be dependent on the number of connections they have. So we know that some have more, some have less. Let's display the network. Can I show you how to do that? Okay, ladies and gentlemen, we're in a race against time here. Go to person. I'd like you, ladies and gentlemen, I'd like you to go to person and choose, you have to scroll up and choose connections, okay? Choose connections. Okay. Now for connections, I would like you to scroll down in connections to the area that says animation. Down at the bottom. Way down at the bottom. Scroll down to where it says animation, and you're going to do draw line connecting agents. Are we okay with that? Okay, so let's now run it. Okay, now we have people in a what? In a network. Okay, we're cooking with gas. Time is a ticking, but I think we're going to be able to thread the needle. Ladies and gentlemen, next, we will put into place a state chart for a person, okay? But before we do that, we're going to go to main, and we will put into place, ladies and gentlemen, we will put into place we're going to put into place a contact rate in main. It's a parameter contact rate. Default value is going to be 1. It's actually going to be a type rate, and its value is going to be 1 per day. Not 1 per second, but 1 per day. And the default value will be 1.0. Contact rate in main. Next, ladies and gentlemen. Next, we'll put in duration of immunity. Duration of immunity. What sort of type will this be? We can make it a time, ladies and gentlemen. Okay? And the time will be measured in days, and the duration of immunity will be, ladies and gentlemen, 45. Something like gonorrhea or chlamydia, which you might posit a certain short-lived immunity, but with gonorrhea, these outer membrane proteins evolve very quickly, and it doesn't sustain persistent immunity. Okay. Next, we're going to put in place the parameter duration of infection. We're getting our ducks lined up in a row, and then we're going to go very quickly and implement the state chart. Duration of infection. Duration. Ladies and gentlemen, duration of infection.
I wondered how many of us are behind.
Yeah, is everybody caught up fully?
Yep.
Okay, the back area here is not.
Sorry?
Sorry, the back area here is not caught up.
Oh, the back area.
Yeah.
Okay. Okay, do you want me to share my current model?
You want to do that? And then you take his model and.
Yeah, that would be good.
Yeah.
Okay. I will do that. Duration of infection will be in days, and that will be 10, and then okay, good. Okay, great, ladies and gentlemen. Okay, so I will go and
20 or 10? He said 10, but he put 20 days.
thank you. 10. That's what I meant. 10 days.
So how long did you put on immunity? How many days did you put?
45.
So
And what is the contact rate name?
1. 1 per day. Okay. So I will put this up on the drive for people to download right now. But I will also rehearse what we've done. Okay. And okay. Lecture. Okay. Okay. Did I not save this to the right folder? Let me do. Oh, come on. Okay, don't give me that. Okay. Okay. Yeah. I have to put it in the right folder. Okay. Here we go. Okay. Here we go. And this will be in days. I'm just saving it to the right folder so I can upload it easily. Okay, here we go, and it's uploaded now. Now, just to rehearse what we've done, all we did is we added a population, we added a presentation to population. We then went to main and we dragged in the population to create a population, dragged in person to create a population. We made the size of that population, Winchell, I think, okay, Alan has it. So the size of that population was given by population size. Size of 100, okay? And then we went to main, ladies and gentlemen, and we went down. We went to main, and I went down and I set the space in network to be a distance space network with a connection range of 75. Okay? And we went and I further, just to kind of show that there was a network there, I went and I set the scale X here and the scale Y for a person. And I ran the model and I saw, oh, there's a network. People are connected to different numbers of people, just that the network is not showing. So what did I do then? I went to person and I set it so that I drew a line connecting agents. Okay? And then I ran it and I saw a network. And then what I did is I went and I added 3 parameters. The first is a rate parameter called contact rate, a per day contact rate. The next is duration of immunity, time parameter 45, and the next is duration of infection, a time parameter of 10. Okay, 10 days. Are we okay?
Yeah, it's just Google opening is
Google downloading is confusing.
Link to agents is under population, under main, or under person?
Sorry, the link. Oh, that's under person. Thank you. So when we go to display this, to want to display the network, you want to go in person connections and scroll down to animation, and you will find draw line connecting agents. Don't do that in main. There's a corresponding one in main, but that'll be connecting up mains, which isn't terribly meaningful. This one is for connecting up people. Draw line connecting agents. Indeed, indeed. Okay, ladies and gentlemen. Okay, we're going to make the push now. We've got over 15 minutes left, and let's make the push, okay? So let's go to person, and let's put into place a variable called color, spelled in the Queen's way. Okay, color. What sort of variable will it be? What sort of variable would that be? Is it a time? Is it a rate? What is it? Is it a double? It's an other, and what is its type? Color with a capital C, spelled according to the dictates of the American Imperium. Okay, the initial value is black. Please set the person's shape body to be colored according to the color. So we just added a color variable, and we want to set the shape body to have a color dictated by the color. How are we going to do that? Change fill color in shape body. Change fill color to be color. Okay? Good. Okay, now, ladies and gentlemen, we're going to put in a state chart. And this state chart will be called the infection state chart. Ladies and gentlemen, it will contain 3 states: susceptible, infectious, and recovered. There'll be no exposed state. And we're going to posit that people get infected when exposed. So we're imagining transmission of an infecting dose here. Tomorrow we'll put into place probabilistic transitions. It's very easily done with a branch. Okay. So we'll have infection state chart. And this, we're going to put in place a susceptible and a infective and a recovered state. Now, the transition, ladies and gentlemen, from susceptible to infective, for now we're going to leave it as a timeout transition. I'm going to call this infection. There we go. Okay, Alan stands ready. Raise your hand if you need to avail yourself of his assistance. Infective to recovered, we're going to have, this will be called recovery, and it will be a timeout transition as given by what? What did we add earlier? Duration of infection, ladies and gentlemen. So, but that parameter lives in main, so we can modify it on a per experiment basis. So this thing, oh my gosh. Okay, this thing, hey, come on. This thing needs to refer to main. For recovery, the timeout will occur at time main dot duration of infection. Okay? Okay, ladies and gentlemen,
For infection, what is the
duration of infection?
just the infection transition?
We're going to leave it just as default for now. We're going to fill it in just a minute. But I just left it as the default values.
Could you repeat the transition to recovery?
Recovery, it's a timeout transition with a timeout being given by main dot duration of infection, because this parameter lives over here in main, because we want to vary it on a per experiment basis. Okay? Okay, next, we're going to add in a waning of immunity transition. Ladies and gentlemen, here we go. Waning of immunity. Waning of immunity. This transition will be called waning of immunity. And ladies and gentlemen, it'll be a rate transition with a mean time of main duration of immunity. So therefore, a rate of being 1 over main duration of immunity. This is just a factoid. If you have a hazard rate with a certain rate, the mean residence time in that state will be 1 over alpha. Put another way, if you have a mean time in a state, the rate from leaving the state, if it's a memoryless process, the rate of leaving the state is 1 over that mean time in the state.
You mean mean time, mean duration, not the main duration. Is that typo?
No, this main is actually referring to the fact that duration of immunity lives in main. Yeah. Just like here, this had to be main dot duration of infection. You're right, this should probably have been called mean duration of immunity to make it clear it's an average. But I've called it duration of immunity. So it's 1 divided by 1.0 divided by main dot duration of immunity. Okay, ladies and gentlemen, finally here, I would like to set the color. So for susceptible, the color is equal to green. For infective, and let's color it visually, green. Oh, not cyan, green. For infective, the color, ladies and gentlemen, is red. And let's assign color to be red. Do we need a semicolon?
Yes.
We do. It's commanding it. Do this. And for recovered, ladies and gentlemen, we're going to have gray. Or this says silver. I want it to be gray. Okay, gray. And here the action is going to be color equals gray. Okay. There we are. Ladies and gentlemen. So what happens if we run the model right now? What do you think will happen? What do you think will happen? What will we see if we run the model right now? So people will be initially susceptible, but then what will happen?
They'll start moving on that timeout of 1.
Yeah. So why do they all get infected at the same time? Because after a timeout of 1, they go from here to here. We haven't yet had infection occurring. So, ladies and gentlemen, now in the closing 7 minutes, 8 minutes, we're going to put into place infection. Okay. Ladies and gentlemen, may I ask you to change something? Instead of being a timeout from susceptible to infective, this will now be dictated by a message, arrival of a message. And for now, it'll be unconditional. Whatever message comes, we're going to do that. Okay? Sorry? Next, ladies and gentlemen, we are going to put in place an internal transition in the infective transition. An internal transition here.
Is that the same as a transition?
Yes, it's a type of transition, but you don't actually leave the state. You just stay in the state.
Grab the transition thing.
Yeah, something's occurring, and this is going to be associated with a rate, and guess what this rate is going to be? Yeah, this transition will be called contact. And the rate at which it occurs is called the contact rate. And where does that live? In main. So main dot contact rate. Okay, now. Getting very close. What has to happen at contact? Well, if someone is infective, in other words, if this goes off, because this is only going to go off when they're infective, what do they need to do? They need to send a message to someone around them.
Yeah.
So this person in the action is going to do this dot send to random connected, a random person connected to them, and the message will be infect. They actually are not going to pay attention to the message, or they're not going to be particular about the message right now. Infect. Okay, great. Ladies and gentlemen, so now what did I do? I did 2 things here. Ladies and gentlemen, I set it so that this is based on a message transition, unconditionally. And second of all, I set it so the contact, there's an internal transition here from infective to itself. In other words, you're not becoming uninfective. It occurs at the contact rate given by this. And in that, they are going to send a message to one of their random connections in the network saying infect. Now, if we run this model, what do we expect to see right now? And I'll go back to that if you want to look at it. Okay, Alan, maybe you could help Dina here. Okay, nothing happens. Why not?
That's what I said, I don't think.
Oh, okay. Yeah, so that's correct. Nothing is happening. Why not?
Something's not there, there's no.
No one's initially infected. So, we have two ways we can do this. Let me show you a way that's a little bit of fun. It also has the virtue of quickness. So, let's go back to shape body. Do you remember shape body? Do you remember how to get to shape body?
Yes, that's fine.
Okay, let's go to shape body and let's scroll down in shape body to, ladies and gentlemen, the advanced section. Okay? Okay, you can pat yourself on the back. You're in the advanced zone. Okay, now this will let us put some code when the person is clicked. When they're clicked, we'll do something. So when we click, we're going to send them a message to infect them. Okay? Okay. This dot, okay, and we could do this in a couple of ways. We could do send myself a message, and I think I'm just going to do that. This send here, I send myself a message, okay? So I'm going to send infect, and I'm just going to send it to myself, okay? I'm going to infect myself. That's not the only way to do it. There's several ways to do it, but that's the way to do it, okay? Or that's one way to do it. Okay, now let's run this model. We can now choose a person at our leisure. So where did I go for this? Ladies and gentlemen, I went to shape body. I scrolled all the way down in shape body to the advanced area where I went to on and expanding advanced if necessary. I went to on click and I put in this code here. Okay.
I went there, but I don't get it on click.
Okay, so now run it. Do we see anything happening? Not by default, but let's click on somebody. Okay. Now do we see something happening? Do you folks see that? Do you folks see that happening? Okay.
Maybe because of the
Does anyone want me to show something?
Sorry, mine froze. Could you go back to where you're doing the infection message, please?
Sure. To go from here to here,
I just want to make sure.
Yeah, that is like.
we made it dependent on a message. We didn't change anything here.
Oh,
It's
it's
unconditional.
Okay.
Next, ladies and gentlemen, we went to contact. We put in place a contact transition. Its rate was given by the contact rate in main. And when this occurred, they sent a message to one of their connections.
Is it in
Okay.
person?
And now, what we did further was to put it so that when clicked on, this shape body down in the advanced area, when we click on them, we send them a message. Now, had I more time, I would show you an additional way to do it by sending a random person in the population. We'll probably see that tomorrow. But what you should see is something like this, right? Where it will spread. You click on a person, it will now spread, and it'll persist for a certain time.
So what does it say?
But then after a certain amount of time, by chance, it will go out.
Why do you have to die down? Look at that.
Yes, it dies out by chance after a while. Just it so happens that people,
Some of them, everyone's gonna get infected.
but sometimes, you know, the only person that's affected is surrounded by people already recovered only, and
Recovered pretty quickly.
well, it depends on how quickly they lose immunity is a big factor. If they lose immunity, some of them lose immunity sooner, they can get reinfected. It'll be based on this duration of immunity, and it's exponentially distributed. Yeah, it tends to die out after a while. Okay, now, ladies and gentlemen, as the final thing, why don't you create a big population? As another experiment, create a, large population and make it a population of size, 1,000, right? Size 1,000. And you can run it. And now you should see a much denser population. And okay, now it's, I think we're going to have to change this whole scale thing. We don't really need that anymore. So maybe we'll change that scale so that they aren't so big. Ladies and gentlemen, and a final thing, I'm going to go to shape body, and I'm going to remove that scaling and just leave it as the default scale. Because I don't think we need them to be so big. They occlude others. So where did I go? I went to shape body. I went down to position and size, and I removed the scale. Scale X, scale Y. And now they will be more clear in their appearance, and we can go infect someone here. And now you'll see an endemic infection starting to assert itself. Small networks, you can get easy die-off. Larger networks, die-off can occur probabilistically, but it's much less likely to occur because there's a large enough group of people. But now you have this network of people circulating. Some of them at any given time are recovered, susceptible in green, or infective in red, and they continue to persist, spreading the infection. And here we are. So a given person here gets infected, susceptible, and then often infected quite quickly again. Okay, ladies and gentlemen, I think that's all we have time for today. I want to thank you for your incredible persistence with this, for your stalwart exploration of this. We now have our first model, and I will post this immediately, okay? So I'm going to go post this as we speak so that you can, if you had any trouble, you can go download it. So I've just posted it again, and I'll delete the earlier version. Okay, so thank you very much again for your persistence.
I don't think it's a big problem. I think it's just how.
Any questions about that? Do you want me to show anything?
Give you a chance to clear your head for a second. Yeah. Sometimes if I stare at them too long, I just have to look away for a while. But yeah, I think that was.
Any questions I can answer?
Sorry, where was that infect on click that we put in? Where did we have to put it?
We had to put it in the shape body because we were clicking on their
It
image.
was under advanced.
And it was under advanced.
Okay.
There's a thing called on click. And this, just like on enter transition, or sorry, enter state or exit a state, this is a handler, meaning when this place is reached, in this case by clicking, we're going to execute this action. Now, we could have done this in a better way. We could have started a certain fraction of the population infective. We could have put it so that we send a message to some designated infective, but here we just did it interactively to get it off the ground quickly and to show you this visually, which can be nice. Okay, so that's all we have time for. Thank you very much. I posted this model. I know it was very quick, and we'll see you first thing tomorrow morning.